In this video, I'm going to go through a series of equations where I show how to solve exponential and logarithmic equations. In this first example, we are going to exponentiate both sides of the equation in order to solve for x. I'm going to look at the base, and the base of this equation is 5. So on both the left and the right, I now have a base 5 and an exponent as shown. On the left-hand side, base 5 and log base 5 are going to simplify to 1, and we bring down what is in back, which in this case is 2x plus 5. 5 to the third is not 15, it's 5 times 5, which is 125. Subtracting 5 from both sides, I get 2x equals 120, and dividing by 2, I have x equals 60. All right, let's look down below at a similar example. Now, what's different in example number 2 is we see no base. When you do not see a number below, it's always going to be a hidden 10. Again, I'm going to exponentiate both the left and the right. So whatever this value is going to become the base and the exponent, the base and the exponent. On the left-hand side, simplifies to 1, and I bring down 4x minus 1. 10 squared is 100. Adding 1 to both sides, I have 4x equals 101, and dividing by 4, I have x equals 101 over 4. I'll move that up so you guys can see the entire process. All right, now in the third example, you see what looks like an ln, standing for natural log. ln is equivalent to log base e. And because natural logs, or ln, is used so often in real-world mathematics, we actually have our own button. You can see it right here. It is the ln key. So I'm going to rewrite this just for the purpose of this problem so you can remember that. ln is the same as log base e. So I'm going to get started on this problem, just rewriting it in an equivalent form. And just like examples 1 and 2, I'm going to exponentiate both the left and the right. The base here is the value e. Remember, e is Euler's number, and it is not a variable. It is a value. On the left here, this is going to simplify to 1, and I bring down 6x minus 2 equals e to the 5th. Now to isolate the x, I'm going to add 2 to the opposite side. These are not like terms, cannot combine them, and I end up with e to the 5th plus 2 divided by 6. Let's look at a few more. The two problems on this page, we are going to see how we can solve equations that have base e, or how we can use natural log in order to solve. So my first goal here in example number 4 is to get e by itself. And just like we think of PEMDAS, please excuse my dear Aunt Sally, when we are solving here, ultimately solving for the variable x, I'm going to go from the bottom to the top. So on the side that contains the variable, is there adding or subtracting outside of this portion? There is. Opposite of subtracting 9 is adding 9. 25 plus 9 is 24. And I'm just working myself up this list. So now, is there a multiplying or dividing? Again, we can divide by 4. Opposite of multiplying is dividing. And then we come to a point that looks very similar to the first 3 problems. So we now need to still solve for x, and I'm left with e raised to this value. So I have an exponential equation, and I'm thinking, how can I use logarithms? So the reason we use logarithms is when we're providing an equation that has a variable in the exponent position and we can't do mental math to solve. I want to give you an example. Here, I meant to make that an x. Here we have a variable in an exponent position, but I can do mental math. I know 5 squared equals 25. Or maybe I give you something similar. Here I have a variable in an exponent position. So I know in this position where x is in the top portion here, in the power position, I can go, okay, 5 to what power equals 125? It's 3. But what if I just gave you this? 5 to what power equals 20? And that's an example when we don't know that exact value because it's not an integer value. There exists a value, it's some ugly irrational value, but we now use logarithms. That's the purpose of logarithms in solving equations. When you have a value in an exponential position and we need to solve and we can't use mental math to do it. So what do? We take whatever the base is the value e, and I'm going to write log base e both to the left and to the right. Remember, whatever you do to the left, we must do to the right to keep it balanced. Whatever we do to the left, we must do to the right to keep it balanced. Now, we also could have written ln here, because remember ln, or natural log, is equivalent to log base e. What does this do for us on the left-hand side? These are going to cancel out, simplify to 1, and I bring down 3x plus 8 equals log base e of 6. Now to solve for x, I'm going to subtract 8 to both the left and right. I want to make sure to put this in parentheses. I don't want you to think those two go together. And then my last step will be to divide by 3. So x equals, now we could write ln, natural log, or we could write log base e, they're equivalent. This is the exact answer to this equation. In this fifth example, notice that we have an exponential form on the left and on the right, and in this case, both of them contain the value e. When we have a situation like this, we are able to solve by eliminating the e's. Now, why can we do that? Because what we really do, we take the log base e to the left and the log base e to the right. Now, what if this was the value 2 and 2? Then we would take log base 2 and log base 2. What does that do? On the left and right, these are going to cancel out. They simplify to 1, and I bring down 5x minus 3 equals 2x plus 9. And then I solve. I'm going to subtract 2x to the left-hand side, and I'm going to end up with 3x minus 3 equals 9. I'm going to add 3 over, and I have 3x equals 12. And then divided by 3, I get x equals 4. Here's another example. An example where we have an exponential equation, but I don't know a value. Like, if I can cover this up for us, 5 to what value equals 23? Well, if this was 25, I'd tell you 2, but 5 to what? I know there exists a number, but it's going to be ugly and irrational. How do I figure out that value? That's when we use logarithms. Whatever I do to the left, I must do to the right. And the base of the log is determined by this value. I bring down 2x plus 6 equals log base 5 of 23. And then I'm going to subtract 6 to the other side and divide by 2 to isolate the x. Log base 5 of 23, subtract 6, and divide by 2. An exact answer. Okay, same concept. I want to solve for this x. 7 to what number equals 12? I don't know. I know 7 to the first is 7. I know 7 squared is 49, and 12 is in between 7 and 49. So it's 1 point something, but what is the value? Let's figure it out. Log base 7 and log base 7. 3x minus 2 equals log base 7 of 12. I'm going to add 2 to the opposite side, and I'm going to divide by 3. And here's my answer. Log base 7 of 12 plus 2 divided by 3.